Welcome to the grandest scale of physics. Throughout your course, you have analyzed the microscopic world of quantum mechanics and the macroscopic mechanics of terrestrial objects. Now you apply those fundamental principles to the entire universe. The central challenge of astrophysics is that we cannot design controlled experiments on stars or galaxies. Our only source of data is the faint electromagnetic radiation reaching our telescopes. In this unit, you will decode that starlight to measure unfathomable distances, determine the physical properties of unreachable stars, and uncover the origin and ultimate fate of the cosmos.
Astrophysics builds a cosmic distance ladder. The first rung relies on standard candles. These are objects like rhythmic Cepheid variables or explosive Type 1a supernovae, which have a known intrinsic luminosity. By comparing this total emitted power to the radiant flux intensity we actually observe on Earth, you will use the inverse square law to calculate the distance to galaxies millions of light years away. Precision with this vocabulary is vital for your Paper 4 marks.
How do you measure the size of a star you can never visit? You model it as a perfect black body radiator. First, you will apply Wien's displacement law to estimate a star's surface temperature directly from its peak emission wavelength. Then, you will chain that temperature into the Stefan-Boltzmann law to calculate the star's actual radius. This synthesis of equations is a classic high-scoring calculation. Just remember, a common trap is forgetting to convert Celsius into thermodynamic Kelvin.
When we look at distant galaxies, their light is stretched or redshifted. You will calculate this redshift to find their exact recessional velocity. This leads directly to Hubble's law, proving that the universe is expanding uniformly in all directions. You will also practice a crucial high-level exam skill, converting the Hubble constant from astronomical units into SI base units, allowing you to estimate the age of the universe in seconds.
Tracing that expansion backwards logically leads to the Big Bang theory, proposing a hot, dense origin point for space itself. Cambridge frequently tests your ability to explain the evidence for this model. You must be ready to write out the exact mark scheme points describing how the cosmic microwave background radiation is the cooled, stretched echo of that initial expansion, providing the ultimate proof that the universe was once infinitely dense.
Yet, our understanding remains incomplete. Look at how stars orbit in a galaxy. Newtonian gravitation predicts their orbital velocity should drop off with distance from the galactic center, but observations show a flat rotation curve. The outer stars spin far too fast. This discrepancy is your core evidence for dark matter, an unseen mass holding galaxies together. Coupled with dark energy driving the accelerating expansion of the universe, these form the most exciting unsolved mysteries you will encounter.
You are now ready to tackle the cosmos. You will measure the universe using standard candles, decode starlight to find stellar radii, and use redshift to prove the Big Bang. Let's take the first step on the cosmic distance ladder.